For a polar curve, r equals f of theta, which is greater than 0. Derive a formula for the area of the region from where the radius is between 0 and f of theta, and theta is between some angles alpha and beta, where alpha is between 0 and 2 pi. So here, let's draw some arbitrary curve to represent f, and let's let the first piece of it that we've got be at angle alpha, and the second piece at angle beta. So our angles are between those two. So if we want to integrate it, we somehow need to break it into small pieces. And the natural way to do it is to take a point from the origin and let it touch the function, and take a little wedge. Do that several times. And ideally, we'll do it very, very many times, but my drawing skills are going to limit us to I'll just make 3 of them. So the first one will be that wedge. Second one will be this wedge that I'm coloring in. Trying to not color over the blue line so we can still see it, but of course the region includes the whole wedge. So outlining them in black so we can see them. We're here. So those are our little pieces that we've broken it into. And let's say that on each one there's an angle of delta theta. And so for each different theta input, we'll have the value of the function. I use kind of left-sided ones, the points on the lower angle version of lower angle side of each little wedge. But that's how it works. Now, what we need to do essentially is to somehow run the number of wedges to infinity and add up all their areas. Now we can't, it's not too simple to do that because we need to somehow write down what the area of an arbitrary wedge is. So if you notice, they're all sectors of a circle, technically. So if I take a circle who has a radius of f of theta at a specific location, let's see, to be careful, let's call this f of theta I, where we'll index the thetas from alpha up to beta. And the little angle that we have has an angle of, the little wedge that we have has an angle of delta theta. So if we want to know what the area of that little portion is. So area of a wedge over the area of the whole circle would be equal to this delta theta, the angle of the wedge, over 2 pi. Because 2 pi would be all the way around the circle. So if I know that the radius is this f of theta I know the area of the circle is 2 pi times f of theta I. Like that. Squared. Sorry, mistake there. Should have been pi r squared for area, so pi times f of theta I squared. If we multiply the denominator over to the right side, I've got delta theta times pi f of theta I squared all over 2 pi. The pi's cancel, leaving us with 1/2 f of theta I squared delta theta. So that's the area of a small wedge. where we're letting this delta theta essentially be beta minus alpha over n, where n is the number of wedges that we're using. In this case, n is 3, but we want to run n to infinity. So what we can say is that the area is approximately the sum, as I goes from 1 to n, of the area of each of the wedges, 1/2 f of theta I squared delta theta. So that's, for large n, the area is approximately this. So for integrals, what we do, we just run n to infinity, and we get the exact answer is the integral from alpha to beta, the values between which theta varies. And then our formula for the area of a little sector goes here. And instead of delta theta, we'll say d theta, which when we're running to infinity, that delta theta gets tiny and tiny and tinier and tinier. So d theta is kind of an expression of that arbitrarily small value. But in any case, this is our answer. This is the formula for the area under a polar curve.